Now another question. Okay, another example. So I have 10 people who reach simultaneously at a museum, and museum allows passes, so they all came with passes. Okay, so you can use the pass to visit regularly, maybe in once in a month you want to go a couple of times, you can use the pass to go. So one day in the morning, when the museum opens, 10 people stand in the front of the museum, and then they all reached at the same time. Okay, so basically when they wanted to enter, so the ticket checker said that, okay, I cannot put everybody together, I want to check passer, so please form a queue, right? So stand in a line and then come inside, right? Now since all of them came together, they can queue in any way they want, right? If some person reached first, then we can say that, okay, because he reached first, he stands in the front. But now here everybody came together, so any order they are going to stand is not going to make a difference. So the question is that how many different ways this queuing can be done. So how will you count this, right? Now if you look at this question, there is see, so we can say that, okay, let us look at the let us look at the first person who is going to be in the line, right? The first person going to be in the line can be any of the 10 persons, right? So I can choose the first person who is going to stand in any of the 10 possible ways. But now when I look at the second person who is going to stand in the line, that is going to depend on who was in the first, right? The choice of the person who is going to stand second is going to be dependent on the who was standing in the first position, right? Because if so A, B, C, D, etc. are the people. If A is standing in the first position, then A cannot stand in the second position, right? But if B was standing in the first position, right, out of this 10 we choose B to be in the first position, then B cannot stand in the second position, so it can be only any of the other guys, right? So the choices themselves are not independent, right? But the number of choices, on the other hand, one can show that it is independent. So the framing of the rule, product rule, is careful, right? So it says that if the number of choices of each separate decision is independent of previously made decisions. So the choices themselves need not be independent, right? So that is important, right? So the first in line, we have 10 possible choices for that guy or that person, right? That girl. So whoever arranged there, one of these 10 persons must stand in the queue. But once a person is decided, the second position can be filled with any of the 9 possible remaining guys. Even though who is going to stand there is dependent on the first choice, the number of persons who is going to stand there does not depend on this choice. So therefore, I can clearly say there are 9 possible other guys standing for the second position. Then I can choose the third guy in 8 possible ways, etc. The last guy is going to be only one guy, right? He is going to stand in the 10th position. So we already said that even though the choices are not independent, the number of choices at each stage were independent. So therefore, I can now take the product. So I can multiply 10 into 9 into 8 into etc. into 1, right? So therefore, the total number of ways to form Q is 10 into 9 into etc. 2 into 1, right? This particular number has so much applications and it comes in so many places in any of the counting questions that it has a special name. It's called factorial. You might already have seen this, right? and it's denoted by 10 factorial in this case, or n factorial if you are looking at n in general. So this particular symbol, exclamation mark. So this is the this is how we. Why is it not coming? This is how we denote. Okay. So fine. Now another example. Okay. So I'm looking at too many examples maybe, but these examples are also telling some other questions that come, some parameters that comes very often. So that might be also useful. So let S be a set which has n elements. Okay. Now a k permutation of the set S are the ordered k element subsets of S. Okay. So I can just take the k element subsets of the set and then order them, right? So we start with a set, take some number of elements from them, put some in any order that I want. Now the question is that how many k permutations of S are there? Now, how do you count this? Well, from the previous question that we looked, we might have a good idea about it, right? So I start with a set S which has exactly n elements. Now I want to form a k permutation, means that I need to order these k elements in whichever k elements I am going to have in a particular manner, right? So I fix, let's say, k positions and then say that okay, the first position I am going to choose, right? So 1, 2, 3, etc. K, right? Now first position I want to fill up with some element, right? So I can choose one of the elements. There are how many choices? There are n possibilities, right? N possibilities for the first position, because any of the n elements can be selected here. But then the second position, the first person whoever I choose cannot be there. So therefore the remaining n minus guys, one of them can be chosen here. Then n minus 2 and then up to n minus k plus 1, right? So if there are k element subset that we are forming, not subset, like permutation that we are forming, then we can choose n persons for the first position, n minus 1 for the second, etc., n minus k plus 1. And each of these choices are independent, so therefore it is n into n minus 1 into, etc., n minus k plus 1, right? Yeah. So this particular thing has a special notation. This is denoted by this n within brackets and then k outside, right, as a subscript. So this is something, yeah, something a notation that will come again, and it's also denoted sometimes as npk or p of n comma k. So all these notations are used, but we will stick with one of them as far as we can. But sometimes many textbooks follow many different notations, and sometimes we might just use one of these. Anyway, it's better to be familiar with this. So this is the number of permutations, k permutations of a set. Now if k is equal to n, right? So we are looking at n minus 1, n minus 2, etc., n minus k plus 1. Now when k is equal to 1, you can see that this immediately reduces to n factorial, right? This is what we get, right? So and it also makes sense because we are talking about k permutations. Now what we looked at earlier was basically an n permutation of the n set, right? Because we are looking at all possible arrangements. This is precisely what we looked at in the previous question, where we're looking at the number of ways to queue up the 10 people, right? So the 10 factorial came because they were all the permutations of the people, right? We were arranging them in a linear order. So the linear arrangements of these objects can also be called as permutations of them. Okay. So, so our observation is that n choose k is n factorial by n minus k factorial, because by definition, whatever n minus k factorial is 1, 2, etc. up to n minus k, their product. And n factorial, it is 1, 2, etc. n. But in the NPK, we have only n into n minus 1, etc. n minus k plus 1. So the 1 to n minus k is missing, so that I can just divide, right, from the whole product. So therefore, NPK is n factorial by n minus k factorial. Okay. Yet another example. I think we are looking at many examples. So what we have here. So I have 2 rooms. Okay. So one room has m people standing inside that room, and the next room has n persons standing there. Okay. Now I ask the question, how many different ways are there for me to ask the people in the first room to queue up, and also at the same time in the second room to queue up, right? So I want the persons in the first room to queue up, and at the same time I want the persons in the second room also to queue up. How many ways we can do? So we already saw that if you have m persons and you want to queue them up, then I can do this in m factorial possible ways, right? M factorial ways I can do this. In the second room, there are n people, so I can permute them in any of the n factorial ways to queue them up. But these two I can do independently, because the persons in the first room are queued up and the persons in the second room are queued up separately. So therefore, there is m factorial into n factorial ways. So the total number of ways to queue up them separately is m factorial into n factorial. Now comes the question, what happens if m is equal to 0? If m is equal to 0, I can still arrange the persons in the second room to queue up in n factorial ways, right? So when I say that people in the first room to be queued up in whatever ways they can, and the second room to be queued up in whatever ways they can, I still want the answer that the n factorial guys who are going to be permitted in the second room are all possible different arrangements of them, right? So I want m factorial times n factorial to be the answer for this, but then I want to get n factorial as the answer, because that is the number of ways to arrange the people in the second room. So therefore, m factorial in the first case, when m is equal to 0, must be 1, right? Because otherwise 1 into n factorial, 0 into n factorial will not be n factorial, right? I want n factorial into something to be n factorial itself. So therefore, m factorial in that case must be also 1. So therefore, we justify the reason we use 0 factorial is equal to 1. Okay. So, the factorial we define by taking product from starting from the number -1, etc. till we reach 1, right, for the integer, positive integer. On the other hand, when it is equal to 0, what is the number? So we can justify using it to be 1. In fact, there will be several other occasions we will see that why it is required to define it this way. But now you have at least some reason to see why. Okay. Now here is a question. A manufacturer uses, let us say, serial numbers of the following form, right? So every product that he makes, he puts some serial number, right? Maybe using for warranty purposes, etc. Now, two uppercase letters followed by 5 digits, and then they are followed by the letters capital M and G or capital M and K. Then this can be followed by, so MG and MK, followed by again 3 digits and one uppercase letter. Okay. So the serial number has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 letters or digits appearing in the form, right? Now, how many possible serial numbers he has at his disposal, right? So he makes these products, every day, maybe thousands of them. Now the question is that totally how many serial numbers he has at his hand, right? Because after some time, if it's a finite number, so after some time it might repeat. So till then, when he can do this, right? Produce many numbers of this form. So this is very easy to compute. I want you to think about this and work it out yourself. Maybe that is a better way. Now, another question. Count the odd numbers with the distinct digits between 1000 and 9999. This is a question I want to discuss because of some interesting facts. But before I discuss, please stop the video and look at this question, think about it, and try to come up with your own answer and see whether it matches with our computation. Okay, so how are you going to count this? So here is how I am going to do it. Okay, so I know that I am looking at odd numbers with the distinct digits between 1000 and 999. So I know that all these numbers has exactly 4 digits, right? So I have 4 possible. This is the wrong tool again. Yes, it has exactly 4 digits, right? Now, since I know that the number is odd, I know that the last digit is going to be either 1, 3, 5, or 7, right? Or 9, of course, yeah. So the last digit has the possibilities 1, 3, 5, 7, or 9. So there are 5 possible choices for the last digit, right? 1, 3, 5, 7, 9, right? Now, the first digit, what is the choice I have for the first digit? The first digit cannot be 0, right? It cannot be 0. Now, it cannot be the digit I chose for the last digit because it needs distinct digits. So therefore, I have 8 possibilities here, right? So other than the first one I chose, I can choose any of the remaining 8, right? So I have 1 to 9. Out of this 9, I cannot choose the one I chose for the uh, uh, position here. So therefore, I have remaining 8 choices. Now, to select the second digit, how many ways I can? Second digit can be any of the 0 to 9, the 10 digits, but I cannot have the first digit as well as the last digit, right? So therefore, 8 choices are there for this. And then for the third digit, I cannot use the first digit, the second digit, and the last digit. Right. So therefore, out of the 10, I have 7 choices here. So now I say that, okay, there is 8 into 8 into 7 into 5, right? 8 into 8 into 7 into 5 possible numbers with this property. Now, you might have noticed that I counted it in a very special order, right? Like I counted the numbers for the last digit first, then I counted the numbers for the first digit, then I counted for the second and third digits. Now, question is that can we do it in another order? And of course, you may be able to do it in another order, but again, you have to be very, very careful. Suppose we did in the other order, okay? Suppose we started with the order that as follows, right? So I start with, let's saying that, okay, I'm going to look at 4-digit numbers. I have these 4 possible positions. The first position can be any of the numbers 1 to 9 because it cannot be 0. So I have 9 choices here, right? Then the second position, it can be 0, right? But it cannot be, it cannot be the number that I chose the first. So there is again 9 choices for this. And for the third position, I have, to avoid these 2 guys. So therefore, I have 8 choices here. Now, when it comes to the last position, what you will say, right? So you have to say that, okay, I have the possible numbers like 1 to 5, 1, 3, 5, etc., 9. And out of this, I want to avoid the numbers that has appeared before. But the trouble is that we don't know whether how many odd numbers appeared here or how many even numbers appeared here, right? I mean, if the first 2 digits were 1 and 7, then I cannot use 1 and 7 here, right? But on the other hand, if it was like 2, 4, and 6 that we are using, then I can use any of the 5 numbers. So I don't know exactly how many possibilities I have for the last choice. This is because the number of available decisions is not independent of the previous decisions, right? So we need to keep the independence, and for that we might have to choose a particular order of computation. So we computed in this order, right? We started with the last position. Then we said that, okay, so I already chose the most restricted one, right? It must be odd. And then I went to the second position, right? And the first position here, because it cannot be 0, right? And it must be distinct from this. And then again, I know that all the things are available or possible here, but except for the 2 which are used here, so I can freely choose. So processing in a different order may not give the independence always. So therefore, we have to be careful in deciding which order we are going to choose, so that the choices, right, at the time we make are independent of the previous. The number of choices are independent of the previous choice. Okay. We are looking at anagrams. So, anagrams are basically permutations, basically words. So given a word, you can permute, the letters of the word in whichever way you want, then to find out different other words, right? They need not make any sense, but they can be, just words, not a word in the particular language, but they are words made from, basically strings made from permuting the letters. So how many words can be obtained by permuting the letters of the word LOCK, lock. Okay, this is easy because as we have already seen, we have four letters here, L, O, C, and K, and we are allowed to use only these four letters. The four letters can be ordered in any of the possible ways, right? So we are looking at permutations, right, for anagrams. So there are four different letters, and how many permutations are there? 4 factorial, right? N factorial permutations. We already saw that. So we can immediately say that, okay, there are 4 factorial, which is equal to 24 different words we can make. So maybe as an exercise, try to write down the 24 different permutations of LOCK and make sure that there are exactly 24 of them. Okay, now I ask, okay, what about LOOK, right, instead of LOCK? Can you use the same argument? Or why cannot use the why we cannot use the product rule to find out the same thing, right? So how do we use product rule here? Well, out of LOCK, the first position can have all the 4 possible choices, right? The second position, once you chose the first one, cannot be used in the second. Therefore, I have 3 choices, then 2 choices, and 1 choice. So why it cannot be used to solve this in this case, right? LOOK. So think about this. Okay, think about this and find out why we cannot use this and why we could use in the previous thing. Okay, so we will stop this lecture at this time, then continue the next lecture. Okay.